Hello, and thank you for tuning in. For this project, we were interested in the effects that non-planar beds have on erosion, both on the dynamics of saltation and the resulting mass loss erosion rate of real rock surfaces. So, we are going to get into the flume with natural sediment and bedrock and see what happens to the motion of sediment and the erosion of bedrock when we introduce roughness elements. I am your narrator, Jeff Larimer. This is what I look like sometimes, and these are my corporate sponsors. Okay, so we are investigating bedrock river erosion by saltating or hopping sediment particles that are transported as bedload. So of course, we are going to consider our experiments and results in the context of the seminal work by Sklar and Dietrich and their saltation-abrasion model, where erosion is equated to the volume of bedrock removed per impact, the impact rate per unit width of the bed, and the fraction of exposed bedrock. In their model, Sklar and Dietrich used a broad data set of sediment transport experiments to derive non-dimensional scaling of sediment impact energy with bed average shear stress. They found that the shear stress of flow along the bed, as the shear stress of flow along the bed increases, the erosion rate decreases. This was due to the average hop length increasing at a greater clip than the increase in average sediment velocity, effectively reducing the frequency of impacts while only marginally increasing the average kinetic energy per impact. Their work forms the mechanistic foundation for bedrock erosion by saltating bedload. The motivation for this project was to put the saltation-abrasion model to the test with respect to how accurate are the predictions of sediment hop motion and do erosion rates scale with impact energy as predicted. We are going to see the results of these analyses for both a planar bed and a non-planar bed, for which we have created subtle roughness elements. These experiments are novel in that we are measuring the sediment velocity upon impact with the bed, which is a static bed surface that undergoes very minor changes where only the rock surfaces erode at small fractions of a gram per hour. In the top two panels, we have the plan view of the flume and the camera and lighting setup that we use to track sediment trajectories. In the bottom two panels, we have the planar and non-planar bed, in which the rock disk samples are either embedded flush with the surface for the planar bed or tilted upstream at 10 degrees from the bed slope for the non-planar bed. We performed 4 experiments in which we vary the bed type and the flow magnitude. Each experiment lasted about 50 hours. This duration was chosen to get measurable mass loss on the strongest rock type in our collection. And in the lower right, you can see a video of the flume at the Center for Ecohydraulic Research in Boise, Idaho. The mean sediment size in these experiments was about 3 centimeters diameter, so gravel, and the average shape of a piece of gravel was a long axis twice the length of the short axis, which corresponds to a Corey shape factor of about 0.5. So in other words, not spherical grains. And during each experiment, we recorded around 200 saltation hops through a viewing window on the side of the flume. We used image processing algorithms to track the path and size of sediment as it traveled through the field of view. We are interested in how these key components listed at the bottom here of saltation scale with bed shear stress. These components are the impact velocity normal to the bed, the hop length, and what I will refer to as the impact energy rate, which is essentially the energy per impact multiplied by the rate of impacts. To compare these saltation components with other experiments, they are non-dimensionalized by their grain size, particle density, and gravitational acceleration. Here we have all of the recorded trajectories for each of the 4 experiments. Planar bed experiments on top and non-planar experiments on the bottom. The gray arcs are the sediment paths in the vertical and downstream direction. The black dots are the non-dimensional impact energy rate values for each trajectory plotted at their x distance, their hop length. As you can see, there is quite a bit of variability in the sediment paths, and saltation paths become more variable over the non-planar bed, which is expected to occur from impacts on roughness elements. We also see that the non-planar bed increases the number of high-velocity, short hops, which is a double whammy because they are high in energy and frequency. Now let's look at the scaling laws within the Saltation-Abrasion model. These are the relations between transport stage on the x-axis and impact velocity in figure A, hop length in figure B, and impact energy rate in figure C. That I'll remind you is a function of both velocity and hop length. The scaling relations from both Sklar and Dietrich 2004 and Auel et al. 2017 are shown by the black lines, and note that their regressions were for planar beds only. Our data is plotted in color. The yellow symbols are the sediment hops from planar bed experiments. The purple symbols are from the non-planar bed experiments, with the velocity component normal to the average bed slope, which is WSI in the diagram to the left, and the turquoise symbols, which are also from non-planar bed experiments, but their velocity component is normal to the tilted disks. In the interest of time, let's just look at the bottom panel. We see that the Sklar and Dietrich relation overpredicts impact energy by quite a bit, and while the magnitude of our impact energies is more agreeable with Auel et al. 2017, we do see a negative relation between impact energy normal to the average bed slope and shear stress for either the planar or non-planar bed, which is consistent with the Sklar and Dietrich model. However, the impact energy experienced by the roughness elements themselves, the turquoise symbols, shows no relation to shear stress. This suggests that simply including the bed surface angle into the kinetic energy equation does not capture the effect on sediment motion, and that subtle roughness elements significantly affect saltation dynamics. Keep in mind that these experiments only test one deviation in bed surface angle, and that more aggressive roughness elements will begin to resist the flow velocity more significantly and may not result in greater impact energy with steeper bed surface angles. But more experiments are necessary to determine that. However, in keeping with the theme of this session, the first thing that I notice when looking at these data is the 4 orders of magnitude in variation around the mean for which we are basing these empirical relations and model predictions of erosion rate. So let's take a look at the distributions of these data. Here I have ranked the data and plotted the fraction of the total impact energy of recorded hops with the fraction of total impacts. We can see that the top 20% most energetic impacts account for 50% of the total energy for planar bed experiments and 70% of the total energy for non-planar bed experiments. This is suggestive of stochastic behavior and approaching the skewness of something like wealth distribution, where the Jeff Bezos of bed load impacts would be this first dot, Jeff Goldblum would plot somewhere in here, and Jeff Larimer would be somewhere way in the upper right. If we plot the logarithms of the ranked magnitude of impact energy rate with the magnitude of impact energy rate, we can see that the tails of the distributions follow power laws. Note that the power law slopes are approaching a value of 3, and at a value less than 3, the statistical moments start to no longer converge to finite values, and impact energy ultimately becomes less predictable. And we see heavier tails in the non-planar bed experiments relative to the planar bed experiments. To try and isolate what part of the hop trajectory is making the non-planar saltations more energetic, I have plotted only the data in the tails in these figures B and C. We see no statistical difference in hop length between planar and non-planar experiments, but we do see a statistically significant difference in hop heights. So while the impact rate is not changing much, the sediment is bouncing higher into the water column and returning with greater velocity. So with this, I figure why not develop a partially probabilistic model and see how it compares with the deterministic model in predicting the erosion rates. So what I've done is taken the saltation component that shows the least dependence on shear stress for both the planar and non-planar experiments, and found the best fitting probability distribution, and replaced that saltation component in the model seen at the bottom. So for the planar bed, impact velocity shows very weak dependence on transport stage and is best fit by a gamma PDF, which is interesting because the downstream travel length of sediment in streams has been found to follow a gamma distribution, beginning with the work of Einstein in 1937. For the non-planar bed, the impact energy rate showed no relation with transport stage and was best fit with a log logistic PDF. Log logistic distributions are more skewed than gamma distributions and are thought to describe systems that are dependent on two competing processes, which in this case could be the effects of hop length reducing overall impact energy and impact velocity increasing the overall impact energy. But it is unclear whether this says something ultimately about the physics of saltation over planar and non-planar beds, or just the flexibility of the log logistic PDF in fitting skewed distributions. So let's see how the erosion rates compare to model predictions. Here we are looking at how the erosion rate changes with hydraulic forcing. So we have plotted the erosion rates from experiments with the same bed type but different flow magnitudes. The black dots are erosion rates in grams per hour. They span a few orders of magnitude due to differences in rock strength. The 1-to-1 line is the solid black line and shows the line of no change in erosion rate between experiments. The dashed line shows the change in erosion rate predicted by our deterministic model, calibrated from the regression analyses. And the dotted line shows the change in erosion rate predicted by our probabilistic model. For these experiment scenarios, there isn't much difference between model predictions, and both models predict the average change in erosion rate pretty well, although there is perhaps a surprising amount of variability in erosion rates. Now, if we look at the effects of different bed types at the same flow magnitude, we see that erosion rates increased on average by 3.5 times for the high flow and 2.5 times for the low flow, which is significantly more efficient than the planar bed. Here, the probabilistic models are much closer to predicting the average change in erosion rate between planar and non-planar beds, but there is a significant increase in the scatter and erosion rate ratios relative to the same bed erosion rate ratios seen in the previous slide. We tried identifying the causes of erosion variability based on where in the flume the rock disk was, or if certain rock types showed more variability than others, but in the end we couldn't find any patterns. So I suspect that what is happening is the volume removed per impact is also stochastic, much like the impact energy from the motion of bedload, where the damaging effects of bedload impacts is a cumulative process in which most impacts remove little material at a time, with rare high magnitude events breaking off much larger volumes. And the tilted disks just increase that upper range of potential impact energies, making the ratio in erosion rate between planar and non-planar experiments shown in these figures that much more harder to predict. I suppose the question is, if we were able to run these experiments for 500 hours or 5,000 hours, would the erosion rate ratios collapse onto a line? I don't know. One thing that we haven't discussed yet is the irregular shape of our sediment and its effect on the impulse of impacts, such as the probability of an impact oriented through the center of mass of a rotating oblong particle. But in the end, I think it's a wonder that despite all of these probabilities involved, from the motion of sediment, the grain by grain breakdown of rock, and the shape effects on impulse, that the predictions of erosion rate are even close, particularly for the experiments shown in the previous slide. I think that just goes to show that the framework of the Saltation-Abrasion model is a solid foundation, but if we want to start to consider the effects of bed topography, which are ubiquitous in nature, we need to start to think carefully about the probabilities involved. Because I'm out of time, I will let you read this final slide, but thank you for watching.